But I did talk about chemical analysis.
Yeah.
So one of the methods of chemical analysis is combustion analysis. Combustion analysis works for hydrocarbons, CXHY. When you burn a hydrocarbon in excess oxygen, what forms?
CO2 and H2O.
Yeah, CO2 and H2O. So if we burn a hydrocarbon like this, all the carbon in the hydrocarbon ends up in CO2, and all the hydrogen ends up in H2O. So if we can figure out how much CO2 we formed, we can figure out how much carbon there was in our original compound.
Oh.
And the same thing with H2O. If we can weigh out how much H2O forms, then we can figure out how much of that came from at least the hydrogen in the original compound. And so that's
That's pretty cool now. My problem was I wasn't doing excess oxygen.
Okay.
I was thinking it was a specific amount, and I didn't know.
yeah, the oxygen is going to end up in both the CO2 and the water.
Yeah.
And that's going to come from the combustion. But we also can combust carbon, hydrogen, and oxygen containing compounds. Carbon, hydrogen, oxygen containing compounds would be like alcohols or even carboxylic acids. You know, carboxylic acids contain oxygen. Or sugars. You know, sugars are going to have. And so we do the same thing here. We're going to form CO2 and water. But here, all the carbon ends up in CO2, all the hydrogen ends up in water, but the oxygen we lose track of. We don't know. The oxygen can end up in CO2 and or water, but the same thing with this oxygen. And so the carbon we can track, the hydrogen we can track, but the oxygen we can't. And we can get the oxygen by doing a difference. So I'll do number 44 instead. The difference between 42, there's no oxygen, or 43. 44, there is oxygen. And so with oxygen, we have to do something a little bit different. But we could also have, just in general, we could have an organic compound that contains carbon, hydrogen, oxygen, and nitrogen or sulfur. These are the elements that can be analyzed using combustion analysis. When we do this, we do complete combustion. You know, so for example, you might have done this in Chem 4 or Intro Chem, and that's a burner. So when we do combustion of methane, we get a nice blue flame like this. However, if you see a yellow flame, it's not good. What is the yellow indicating?
Not complete combustion.
Yeah, it's incomplete combustion.
And you're getting is it carbon dioxide?
Well, we're getting carbon dioxide, yeah, like we should for complete combustion, but we're also getting carbon monoxide. So you don't want to leave it yellow like this for a long time. If you do, you're going to get carbon monoxide poisoning and you could die. And the carbon monoxide is not the yellow stuff. What is the yellow stuff? Carbon. Yeah. And so what we're getting here is incomplete combustion. So we got to make sure we get complete combustion here. And so let's briefly talk about combustion processes. Combustion is what we call a redox reaction. In a redox reaction, we need an oxidizer. Well, the prototypical oxidizer is oxygen. And oxidizers like to do what? Take electrons. So oxidizers love to take electrons. Now, how many electrons does each oxygen want? 2. And where did you get that number from? Yeah, from the periodic table. If we take a look at the periodic table, oxygen has 8 total electrons, 6 valence electrons, and it wants a total of how many? 10. And so if oxygen were to gain 2, it would have 10 electrons like neon. On the other hand, oxygen can lose how many? Max. So this is what we call the range of the oxidation state. So normally oxygen has 6 valence electrons or 8 total electrons. But oxygen would like to get how many valence electrons? Well, neon has how many valence electrons? 8. Neon has 8 valence electrons. And so on the one hand, oxygen can take electrons to go from 6 to 8. In the process, it gains 2 electrons. And so oxide would have 8 valence electrons, 10 total electrons like neon. On the other hand, we can go the opposite direction and be like, what? Not neon, but what's the other noble gas nearest to it? Helium. And so helium has how many valence electrons? 2 valence electrons. And so oxygen could lose 4. Well, oxygen plus 4, you don't ever see that. It's not going to be that stable, but we could write it as Roman numeral like this. Sometimes we do that. And so the range of oxidation states that you observe for oxygen are from plus 4 to minus 2.
So for the oxidation of oxide, what I noticed is it's different with the superoxide. Why is that?
The oxidation state?
For a superoxide.
Yeah. Well, oxygen wants 2 electrons, but sometimes it can't get it. Depends on what it's oxidizing. If it's oxidizing a hydrocarbon, no problem. It can take it. But sometimes it can't quite take that many electrons. And so if it can't reach all the way to minus 2, it might stop at 7. What has 7? Fluorine has 7 valence electrons. And it might not make it all the way there. It might just go to this, O2 2 minus. O2 2 minus is called peroxide. And what's the oxidation state of each oxygen in peroxide? Minus 1. So in this case, it didn't quite make it all the way there. Is peroxide stable? Peroxides are not stable. Are oxides stable? Like rust, iron oxide? Is this fairly stable? Yeah. And so here, it's not quite, it needs 1 more electron, each oxygen. So it needs a total of 2 more electrons. Well, it might not even make it here. It might make it just to here. This is a weird one. This is O2 with a negative charge. So O2 2 minus, this is called peroxide. O2 minus is another one, but I'm not making you memorize it. It's called superoxide. What's the oxidation state of oxygen in superoxide? Minus 1/2. And so one way of visualizing that is it's minus 1 on one oxygen and 0 on the other. That gives us an average of minus 1/2. And so minus 1/2 is not quite all the way there. And so this is what we call the oxidation state range. So superoxide is very reactive. It wants more electrons. Peroxide is very reactive. It wants more electrons, right? On the other hand, it could lose electrons, too. And so this is the range of oxidation states that we see, from plus 4 to minus.
I thought it was -2 to +6? Because if it's oxygen +4, wouldn't it be like at beryllium?
Oh yeah, you're right. It doesn't quite make it all the way there. It's -2 to +6. It's got to lose all its valence electrons. So helium, this is tricky because I should probably do it like this. Rather than doing valence electrons, I should rather do total electrons. Because we know there's something special about having 8 valence electrons. It's called the octet. And so using total electrons, neon has 10 total electrons, helium has 2, and technically then helium would have 0 valence electrons in this shell. And so I should have written 0 here, but it's all right. And so we're going from 2 to 10. We're at 6. So actually, we're not at 6. We're at 8 because oxygen has 8 total electrons. So it can gain 2, or it could lose 6. That's the range. It might not gain 2. It might only gain 1/2, like 1 on one, 0 on the other. Or it might gain 1. But here, gaining 2 would be the best. Oxygen doesn't like to lose electrons, because it's electronegativity. But sometimes, it can. Like here, OF2. What would you call OF2? How would you name it?
Oxygen difluoride.
Oxygen difluoride. In oxygen difluoride, what is the oxidation state on oxygen? +2. Fluoride is -1. Fluoride's more electronegative. It's going to take the electron first. That means oxygen's going to lose. It's going to lose 2, so it's +2. So oxygen difluoride, maybe it should be pretty reactive, because oxygen doesn't like to lose. The more electrons you try to take from oxygen, the less happier it becomes.
So when it comes to electron rich or electron poor, it depends on where the oxygen is.
Yeah. No, it depends on where you are in this range.
In this range, yeah. So what would be an example of it being electron rich or poor?
Electron rich and electron poor not only depends on the range, it also depends on what element you're talking about. Because I wouldn't consider oxide electron rich. I wouldn't consider oxide electron rich because it's happy as is. And even though oxygen, O2 is 0, I wouldn't consider it happy as is. Because oxygen is very reactive. So if we look at O2, the 0 is quite reactive. And so it depends on what element we're looking at. And so I call O2 with the 0 charge electron poor, because oxygen is the prototypical oxidizer. Oxygen wants to do what? It wants to take electrons. And it's going to take electrons from easy pickings like metals. Metals are easy pickings because metals have lots of loosely held electrons. So oxygen wants to oxidize metals, take those electrons. And so in that sense, oxygen's electron poor, and anything higher like this would be electron poor, more severely electron poor. So I expect this to be reactive. It's going to want electrons. Whereas something like sulfide, I need a new pen. Something like sulfide is electron rich. Have you ever heard of the sulfur bacteria? There's some kind of bacteria that lives near geothermal vents. You know H2S, hydrogen sulfide, is that rotten egg odor. This stuff is very toxic, but this is food for a certain type of bacteria. We don't eat it though, but it's food for certain types of bacteria because the sulfide is electron rich, and it can be oxidized. So here we have this Wikipedia article, microbial oxidation of sulfur. That's actually of sulfide. Either in the form of H2S, hydrogen sulfide, or HS minus, hydrogen sulfide ion, or even elemental sulfur can be oxidized. But a lot of these live near vents, seaside, underwater vents that spew out some hydrogen sulfide. Thiosulfate is also a good. I told you thiosulfate is a good reducing agent. It's not because of the oxygen. Oxygen is not considered electron rich in thiosulfate. It's one of these sulfurs, not both. It's just one of these sulfurs is electron rich. So sulfur is the same family as oxygen. So sulfur ranges from -2 to +6. When oxygen is -2, I consider what we call electron happy. So oxide's happy as is. Oxide's not electron rich. There aren't bacteria that eat oxide. There are bacteria that eat sulfides though. And sulfide's considered electron rich, but then you go, well, both of them are in the same family, one. And number two, both of them have the same charge. So why do I call sulfide electron rich and oxide just electron happy as is, unreactive?
Maybe because sulfur is less electronegative, so it holds on to electrons less tightly.
Okay, that's one way of putting it. Another way of putting it is this. What makes it less electronegative?
The electrons on the valence shell are further away from the nucleus.
Yeah. And so when I compare sulfide, sulfide's a big ion. Oxide is bigger or smaller than sulfide?
Small.
It's smaller. So if you're trying to pluck the outermost electron, which one is easier going? Which one's going to be easier to take that electron from? The big sulfide or the oxide, the smaller oxide?
Sulfide.
The sulfide. And so this is much easier to oxidize. That is, these electrons are more loosely held, and therefore we would consider this electron rich. And so when we do electron rich and electron poor, we do it element by element, and then we look, the charge. So for example, a -2 here might not be equivalent to -2 here. And a +2 might mean totally different in different cases, So anyway, when we do combustion analysis, we want to do complete oxidation. That's the best. And so we don't want this to happen. So for example, when we burn our hydrocarbon, CXHY, we don't want that yellow flame. Because the yellow flame means not an excess of oxygen. The yellow flame means this is from the Chem 4 quiz question. And you're supposed to cross out excess and replace it with yellow flame does not mean an excess of oxygen. It means limited amount or lack of oxygen. And so not enough. The lack of O2. If we have a lack of O2, we aren't going to have complete combustion of this. And so, for example, methane. Methane is very electron rich. Methane has the oxidation state on carbon of -4. -4 on carbon is electron rich, so oxygen is going to have a lot of electrons to take. And if it just takes 4 of the electrons, we end up with soot. If it takes 6 of the electrons, we end up with carbon monoxide gas. Because 6 of the electrons will take us to +2. So we go from -4 to 0 to +2. That's 6 electrons. But really what we want to do is we want to take all of the electrons. If we take all of the electrons, we go all the way to all the valence electrons, +4. And so that's losing 8 electrons. So -4 to 0 to +4. This is incomplete combustion. Gabe asked me about the question, what about, can I have like extreme combustion? So for example, if I did extreme combustion, can I have carbon trioxide? This is carbon dioxide. Can I go extreme and go carbon trioxide? Yes or no? Would carbon trioxide potentially be a product of combustion?
No.
This is excess, but what if I had a super excess of O2? Could I get carbon trioxide? No?
I don't think carbon can hold that many oxygen.
Why not? Well, let's
Well, if each oxygen takes, I was thinking each oxygen takes 2 electrons, but
Yeah.
they could take less than that, maybe.
yeah, they could take less than that. But if each oxygen takes 2 electrons, what would that leave carbon?
+6.
+6. Is +6 a viable oxidation state for carbon? No. The range goes from +4 to -2. So if we're getting to +6, we're losing valence, not valence. It's okay to lose valence. Instead of valence electrons, we're losing. There are valence electrons and there are the other type of electron.
The inner shell.
Yeah, inner shell electrons are called, not valence, they're called, starts with a C.
Is it central?
Yeah, you have the outer valence electrons and the inner core electrons. So you're losing the core electrons. That's not unlikely to happen. So carbon trioxide we don't expect as a product ever because that's beyond what we expect for the oxidation state. It'd be way too reactive.
So when you're talking about hydrogen, it could be either a +1 or a -1, correct?
Yeah, or 0.
Or 0. And that's when it bonds to a metal versus a non-metal.
When hydrogen bonds to metal, it usually goes negative because metals are electron rich. And so hydrogen can either gain 1 to be like helium or can lose to be like nothing. But typically it loses, but it can also gain. But it can only gain from things that lose their electrons very easily. So metal hydride's pretty much it. And it's pretty much only the group 1. The group 1 metals lose the electrons the easiest because they're the biggest. The bigger atoms are easier to steal electrons from. The smaller ones are much more difficult to take electrons from. So I don't think carbon trioxide is a viable product of combustion because of this +6. So one year I put that on the test. Somebody Googled it after the test and said, oh, there is carbon trioxide. Well, yes and no. What they found was this. When we have an oxygen-oxygen single bond like this, you know what we call that bond? A peroxide bond. And peroxide bonds are not very stable, so they didn't find carbon trioxide, they found a peroxide. Peroxides are quite reactive. And so it's not really a product. There are a lot of things that happen in the flame. Although carbon trioxide can form in the flame, you know, the flame chemistry is a lot trickier to map out. And so one thing is we don't want this yellow on a nice blue flame. The other thing is, what is the blue? Is the blue the water?
It's unburned. Wait, no, it's base. That's the unburned.
At the base is unburned gases.
Yeah, that's cool.
So it wouldn't be unburned gases because methane is not blue and oxygen is not blue. So what is the blue? Well, there's a lot of stuff happening in the flame that you don't see, but by the time it gets up here, what are we left with? By the time we get up here, all that's left is CO2 and water, but in the flame itself, there's much more complicated chemistry. And so in the flame, you could form reactive species like this, peroxide type thing, and you can form atomic oxygen. Atomic oxygen, that's what's giving the blue color. You know, in atomic oxygen, electrons get excited to higher energy levels. When they drop back down, they emit the blue light. And so that's what we're seeing. Yeah. Should I write atomic oxygen as a product here? No. I don't write it. And so we want complete combustion, otherwise things get misty. But we can also analyze things that contain nitrogen. When nitrogen combusts, we oxidize it. Nitrogen, what's the range of oxidation states that we expect for nitrogen?
-3 plus 5.
Yeah, nitrogen has how many total electrons? 7. So we can go to neon, which is 10. And so if it gains 3 electrons, we go to -3. Or we can drop back down to helium. Helium has 2. And so to go from 7 to 10, we gain 3. To go from 7 to 2, we lose 5. And so it's -5 electrons. And so the range of oxidation states will be +5 all the way to -3. +5 here. Helium should have been up here. So +5 to -3. If it's +5, then we could have something like this. N2O5. What's this called? Dinitrogen pentoxide. What's the oxidation state of oxygen? -2. -2 times 5 is -10. We need +10, but we have 2 of them, so each one must be +5. So 2 times +5. So dinitrogen pentoxide. That would be complete combustion of nitrogen. But getting nitrogen to the +5 isn't so easy. You know, because oxygen, yes, oxygen's a great oxidizer, but look at it. Look where nitrogen is. You know, is nitrogen really that weak, you think, in comparison to oxygen? Okay, nitrogen's going to say, okay, here, take all my electrons. Or do you think nitrogen is going to put up a little fight? Because when we think about the electronegativities, what are the 3 most electronegative elements on the periodic table? Fluorine's number 1, oxygen's number 2, and then nitrogen's number 3. Yeah, those are the 3 most we consider. And so nitrogen's not so easy for oxygen to take all 5 electrons. And so what we end up with in combustion analysis, if we have nitrogen in the compound, we end up with NO2. NO2 is not complete. NO2 is incomplete. What's the oxidation state of nitrogen in NO2? plus 4. So we don't quite get to plus 5. And so it ends here at NO2. However, sulfur is smaller or bigger than nitrogen? It's bigger. Sulfur is bigger. Sulfur is easier to oxidize. And so if sulfur is completely oxidized, what forms?
SO3.
SO3. Sulfur trioxide. That's because sulfur can lose up to 6 electrons. And so this is sulfur in the plus 6 oxidation state. This is minus 2. Did I talk about this stuff before? No. And so if there's any sulfur in this compound, it's going to form sulfur trioxide. If we can capture the sulfur trioxide, weigh it, and then analyze how much sulfur there was in here, all that sulfur came from here. And the same thing, if this compound contains any nitrogen, it's going to end up as NO2. And I can capture the NO2 and analyze that to figure out how much nitrogen was in our original compound. And the carbon and hydrogen, we can do the same. Oxygen is tricky because we're burning these in oxygen, so we're adding oxygen. And so let's take a look at a problem here. And, analyze this using combustion analysis. Normally in stoichiometry, we need to start off with a balanced chemical equation. Here we don't have the balanced chemical equation, but we make an assumption in order to solve this particular problem. And so this is number 44. Paracresol is used as a disinfectant and in the manufacture of herbicides. A 0.4039 gram sample of this. Okay, we have 0.4039 grams, and it's a carbon, hydrogen, oxygen containing compound, CXHYOZ. This is combusted in excess oxygen and yields CO2. And they capture and weigh it. And it's going to weigh 1.1518 grams. And H2O. This can be captured and weighed, 0.2694. Did I do this problem? Yeah, no.
It is a homework problem.
It is a homework problem? Oh. Did you already do it?
No.
All right, let's do this problem. The first thing is the analysis for carbon. All the carbon in the original compound ends up where?
Carbon dioxide.
In carbon dioxide. So even though I don't have the balanced chemical equation, I know that any carbon in carbon dioxide all came from the compound. And so that's the assumption. So I don't need the balanced chemical equation. I just need to know it all came from there. And so this is the way we analyze it. 1.1518 grams of carbon dioxide. And then I calculate the molar mass of carbon dioxide. Carbon is 1201. And then I have two oxygens. Oxygen is 1600, so that's 3200. And so CO2 is going to be 4401. And so 1 mole of CO2 weighs 44.01 grams. And so grams of CO2 cancel. That leaves me with moles of CO2. And from moles of CO2, I can go to moles of carbon. Because in 1 mole of CO2, there's 1 mole of carbon. And so the conversion here would be 1 mole of carbon for every mole of CO2 that forms. Now, formulas are mole ratios. And so what I'm going to do is I'm going to do a branch here. On the top branch, I'm just going to calculate the moles of carbon. So let's go ahead and do that. (1.1518) divided by 44.01. 0.02617. I'm allowed. Oh, this is 5 sig figs. Shoot. In my molar mass, I should have went to 5 sig figs. Well, we'll just go with 4 for right now. I'll carry 1 extra. 1. And so formula is a mole ratio, but we can't stop here. We have to do one more step. And one more step is we're going to calculate how many grams of carbon there are. And so the molar mass of carbon is 12.01 grams per mole of carbon. And so I'll take this and times by 1201, and I get 0.31431 grams of carbon. Okay, a formula is not a mass ratio, so why am I calculating the mass? The reason I'm calculating the mass is that's how we're going to figure out how much oxygen we have in this compound. And so we have to do this extra step. Okay, I'm going to do pretty much the same thing with the water. I have 0.2694 grams of water. And then 1 mole of water. Well, hydrogen's 2 hydrogens, 2O2 plus 16 is 18O2. And so this is going to be 18O2 grams per mole. Okay, and for water, we have 2 moles of hydrogen for every 1 mole of water. Okay, and again, I have to do this branch. So normally I stop here to get the formula. So it's 0.2694 divided by 18.02 times 2. And I get 0.029900 moles of hydrogen. But I need to figure out how many grams of hydrogen I have. And to do that, I'm going to use the molar mass of hydrogen, but I'm going to use the 1.008 grams of H per mole of H to get 4 sig figs. If I use just 101, I wouldn't get the right number of sig figs. So times 1.008, I get 0.030139 grams of hydrogen. Now, for the oxygen, I have 0.4039 grams of CHO. And then what I'm going to do is I'm going to subtract the C. So that's going to be minus 0.31431 grams of C. And then I'm going to subtract the hydrogen, minus 0.030139 grams of hydrogen. And so if I take my carbon, hydrogen, oxygen, subtract out the carbon, subtract out the hydrogen, all I'm left with is oxygen. So let's go ahead and do that. 0.40398, or 39 grams, sorry. 0.4039 minus 0.31431 minus 0.03039. And I end up with 0.059451. How many decimal places? I'm allowed 4 decimal places. Grams of oxygen. 4 decimal places will only leave me with 3 sig figs. Okay, now I'm going to go to moles of oxygen. And so I'll go ahead and multiply this by 1 mole of O per 16.00 grams of O. So divided by 16 equals, and I end up with 0.003715. I'm only allowed 4 sig figs. 371,569 moles of O. So formula is the simplest mole ratio. So let's go ahead and get the mole ratio here. The other thing is the previous problem asked for the percent by mass composition. So the percent by mass composition, let me just say something about that here, and then we'll move on, is you take the grams of carbon divided by the total grams times 100%. That gives us the percentage carbon. And then you take the grams of hydrogen divided by the total mass, this one, times 100%, and it gives us the percent hydrogen. We can do the same for oxygen. We aren't going to do that in this problem because they aren't asking for the percent. Or they are?
Yeah.
Oh, shoot. They're asking for the percent. Okay, so the percent, this is by mass, is equal to 0.31431 grams of carbon divided by the total mass, which is 0.4039 times 100%. .31431 divided by 0.4039, 77.818% carbon. And we'll look at the hydrogen percent by mass. .03 0.03139 0.30139 grams of hydrogen, 0.4039 grams total, times 100%. .4619% hydrogen. And then finally the oxygen percent mass. Is 0.059451 divided by 0.4039 times 100%. .719% oxygen. So these should add up to 100%. So let's see if they add up to 100%. So I'm going to take 77.818 plus 7.4619 plus 14.719. And I don't. I get 99.9989%. So what else is in here? Am I missing something? Or is that close enough?
I think it was round off.
Yeah, this is due to rounding error. And so it should add up to 100%, but it doesn't because I had to round it. I couldn't carry all the digits. If I could carry all the digits, then it'd add up to 100%. That makes sense? Okay. So they will also want the empirical formula. The empirical formula is the simplest whole number ratio. Simplest mole ratio. The simplest mole ratio. Well, how many moles of carbon? 0.026171. How many moles of hydrogen? 0.02990. How many moles of oxygen? 0.0037159. Well, that's not a simple whole number ratio, so we need to get a simple whole number ratio. What do we do next? Divide by the smallest number, so that would be this one here. 26171 divided by 0.026171 divided by 0.026171. And so the carbon is going to come out to 1.000. The hydrogen will come out to, let's go ahead and do that, it's 0.0299 divided by 0.02617. 1.142, and the oxygen comes out to 0.0371569 divided by 0.02617. I think I miscalculated. Actually, I didn't.
Is it actually in the smallest number?
Oops. I didn't divide by the smallest number, did I? No, oops. I see my mistake. The smallest number was not 0.026171. What was the smallest number? Yeah, shoot.
These ones are tedious. With all the numbers.
Yeah. If you excessively round off, then you get significant round-off error. And so it's tedious because I'm carrying extra digits, but it's useful to carry extra digits in doing these. Sometimes people get some weird empirical formulas by overzealous rounding. And so the oxygen is 1.00. We're only allowed to use it. The hydrogen, let's figure that out next. 0.0299 divided by 0.00371,569. Must have made a mistake. What are you getting?
8.0469.
8.0469. All right, we'll just go with that. 8.046. The carbon?
7.0433.
7.0433. All right. Then we ask ourselves, should we round it or should we multiply it by some factor? What do you think? Is this close enough to 7? If this were like 7.4, then I'd start to worry. Or if it were 7.5, I would definitely multiply it. Even 7.4, I'd probably multiply it. But in this case, we'll just say C7H8O.
Now we compare the mass to what they give us.
Yeah. And so this is the empirical formula. It would be the simplest whole number ratio. And what I do is I calculate the mass of this, the empirical unit. How much does the empirical unit weigh? And so that means I have 7 carbons. That's 7 times 1201, which is equal to 7 times 10 is 70 plus 14 would be 84. 8407. 8 hydrogens at 101 This is going to be 808. And one oxygen at 1600, which is just going to be 1600. And so the empirical mass is 8407 plus 8.08 plus 16. And the empirical unit weighs 108.15 grams per mole or U per molecule. They give us the molecular mass. The molecular mass is 108, which means a single molecule of this weighs 108. If a single molecule of this weighs 108 and the empirical unit weighs 108, then we know that the empirical unit is the same as the molecular unit. And therefore the molecular formula and the empirical formula are the same. Usually what happens is the molecular mass is twice as heavy. If it's twice as heavy, then we have to double the empirical unit, or 3 times as heavy. We have to triple the empirical unit.
There was one where it was like half as heavy.
A half?
Mm-hmm.
Then if it's a half, then I don't think it's the empirical unit then. Because you can't take half the empirical unit, you'd end up with fractions.
And that would be going backwards. That would be like if it gives you the molecular.
Yeah, they must have given you the molecular and then figured out the empirical from that. So this is equal to the molecular formula because the masses are the same. Uh-huh.
Is there a way to get the molecular formula without any of knowing the molecular units of the compound? What I mean is,
No.
so we
There are other ways, we could put it in a mass spectrometer or do different things, but if you're doing combustion analysis, you need to be given the molecular mass or the molar mass. Here they give us the molecular mass. In the previous problem, what did they give us? Here they give us the molecular mass, 106. Here they don't give us anything, but they only tell us to derive the empirical formula, not the molecular formula. Otherwise, we wouldn't be able to do it.
so in order to say transform from molecular to empirical to molecular, I need necessarily the molecular unit.
Yeah, the molecular mass. Otherwise, you can't figure it out. Here in 46, they have carbon, hydrogen, sulfur. So when you burn this, we end up with CO2, H2O, and in this case, they aren't burning it completely. Actually, they're only going to, maybe I was wrong with this one then. That's not complete combustion of sulfur. If we go to SO2, SO2 is stopping at sulfur what? Yeah, that's sulfur plus 4. This could go all the way to SO3, which is sulfur plus 6. But maybe the same thing's happening here. The same thing as in nitrogen. It's stopping at partial combustion. That's because it's too hard to get it all the way to here. Does that make sense? And so here, well, if we stop at SO2, that's fine. We just need to know where we're stopping at, SO2 or SO3. Okay, this is a conceptual problem. Another conceptual problem. Here, this is burning sulfur. It's going to SO2. So it's wrong. It goes to SO2, not SO3. So you can correct that. And so it's partial combustion. But under certain conditions, we can always get a consistent partial combustion. So for example here, when I get the yellow flame, do you think I'm getting any carbon dioxide or is it all carbon monoxide and soot? When I'm getting the yellow flame here, it's a mix. I get carbon, soot, carbon monoxide, and carbon dioxide. And so when we try to completely combust the sulfur or completely combust the nitrogen, we always end up stopping here. And so it's much more consistent with the nitrogen and the sulfur. It doesn't go complete. Okay, were there other questions?
For the oxidation states, there was one that I want to see if there was a typo or not. For 52E,
Okay.
they're getting a negative, but I'm getting a positive.
On the oxidation state for sulfur,
Yeah,
what did they get?
they're getting a negative 2.5.
Negative 2.5.
Yeah.
What did they get for oxygen?
I don't think they solve for oxygen. They just solve for sulfur.
We're only asking for sulfur.
S4O6 2 minus. So which one did you assign first?
When you say assign first,
According to the rules.
yeah, that's where like I'm trying to wrap my mind around assigning.
Assigning is just based on following the steps. Like it's not hard to remember. First goes the alkali metals. That's number one. All the alkali metals get +1. And then goes hydrogen. Hydrogen gets +1. And then pretty much fluorine gets, oxygen gets, and nitrogen gets -3. That's the rules. But the thing is, sometimes what happens is this. Sometimes things don't get the preferred oxidation state because the number one rule is that all the oxidation states have to add up to the net charge on the species. So we have to go in sequence here. So if you did oxygen first, you could screw this up. Because if we did oxygen first, oxygen would get -2. And that means hydrogen would be, well, if oxygen is -2, hydrogen must be +2 in order to add up to 0. But it's impossible for hydrogen because hydrogen only has 1 electron. And so the max charge on hydrogen is +1. It can't go to +2. And so this is why we need to do it in the sequence. Alkali metals first, and then hydrogen. Hydrogen gets, and then fluorine, and then oxygen. But when we get to oxygen, oxygen can't be -2 here. It won't add up. And so oxygen must be -1. And therefore we end up with peroxide, hydrogen peroxide. Peroxide bonds are so weak, light breaks them apart. And so hydrogen peroxide is not stored in a colorless bottle like this. Because colorless bottles, visible light can pass through. If visible light passes through, it strikes this bond and breaks it. So hydrogen peroxide is stored in a black bottle or amber bottle or brown bottle, something that absorbs visible light. And so here, what gets assigned first? Alkali metals, hydrogen, fluorine, oxygen, nitrogen. So just remember that sequence. And so what would get assigned first would be at and so there are different ways of doing this. 4 times X, where X is the oxidation state on sulfur, plus 6 times minus 2 is equal to minus 2, the net charge. And so that gives me 4x minus 12 is equal to minus 2. And then add 12 to both sides. So 4x is equal to 10. And then x is equal to 10 fourths,
2.5.
which is 2.5.
Yeah, they got negatives, so
I don't know what they did, but negative 2.5 is wrong. Positive 2.5 is correct. That's the average oxidation state on the sulfur. So what we likely have here is we have a mixed charge on the sulfurs. That is, some sulfurs might be +2, other sulfurs might be +3. And so we'll have mixed charge. We can figure out what the charges are if we look at the full structure. Sometimes we get mixed charges. Like, did I do acetic acid?
Yeah.
The average charge on carbon and acetic acid was 0, but when we looked at the structure, the charge, one carbon was -3, the other carbon was +3. And geologists know Fe3O4 as magnetite. What is the charge on iron? What is the oxidation state on iron in magnetite? So we'll do the same thing. We'll call it iron X. Oxygen is -2. So we got 3x plus 4 times -2 is equal to 0. Magnetite's neutral. And so this is 3x minus 8 is equal to 0. 3x is equal to 8. X is equal to 8 over 3, which is 2 and 2/3. And so iron is 2 2/3. This is the common name for magnetite. What is its other name? So should we call this iron, Roman numeral 2 and 2/3 oxide? No, it's not. What it is it's what we call mixed cation, the charge. And so if we investigate this further, Fe3O4 consists of an iron 3+, an iron 3+, and an iron 2+. And then the oxides are all 2 minuses. And so over here on the left, we have a -8 total net negative charge. Over here on the right, we have +8. And so here we have 2 iron 3s and 1 iron 2. And so you aren't going to learn how to name this. This is the wrong name. So what some people are saying is, let's forget this Roman numeral stuff, and we're going to name these like we name binary molecular compounds. This is not a molecular compound. Molecular compounds typically consist of nonmetals, but some people want to name this as a binary. That way we wouldn't make any mistake. And so this would be called tri-iron tetroxide. So tri-iron tetroxide, you're going to get the formula 100% of the time. You know? Otherwise, the name becomes cumbersome. You know, di-iron 3, mono-iron 2 oxide, or iron 3, iron 2 oxide.
When it comes to formula names,
Mm-hmm.
you know how we have a bicarbonate
Mm-hmm.
and we have a bisulfite?
Mm-hmm.
Okay, because they have it as hydrogen sulfide.
That's fine. That's another name for bisulfite. Another name for bisulfate is hydrogen sulfide. HSO3 minus. Good. So you could use either. Okay, other questions?
When we did these questions early on, ones that we are assuming variables. I don't know this because like might just not be comfortable picking a number and putting it in there. I just am not 100% understanding how to do that. Like I know we did one for like chapter 1, number 74.
Mm-hmm.
I just don't think on my own without the book on that instruction, just pick a number. I think I get stuck on
There are a couple of different scenarios when you pick a variable. One scenario is if you're missing something but you know roughly what it is. So let's say you're missing the density of water, but you know roughly what it is. What is the density of water? 1.00? 1.00 is being a little bit too precise. I would probably go with 1.0. Versus looking it up. If we look it up, then we pinpoint it. Maybe it's 0.998756, whatever, but we're just going to estimate it. The other variable is how long does it take you to drive to school? How long does it take you to drive to school? Well, it depends, if there's traffic or detours or whatever. If there's no traffic, let's say you drive to school at 2 a.m. versus driving to school during, rush hour. And so those are variables that you pick. At the longest, it takes me this many minutes. At the shortest, it takes me this many minutes. And so that's a variable that we would pick if it's not given, what the level of traffic is. And sometimes that happens. And so somebody might say, how long does it take? And then you might have to fill in some details there. Otherwise you can't really answer the question. And so if you can't answer the question because something's missing, then you just kind of estimate this one value, like the density of water is this, or you might give a range. If you knew the range, let's say the density of water varied from 1.000 at the highest down to 0.96 at the lowest, then you'd say, well, when the density is at 1, we get this answer. When the density is at 0.96, we get this answer. And so that's the expected range of answers you get. If it's not specified, depends on how precise you want to be with that. But if you need to be very precise, that's what you do. I mean, otherwise you can't answer the question because something's missing. And so, so one example of that I gave, this is a Chem 4 question I gave, was they needed the density of seawater. I didn't give it to them.
But you can assume seawater is the same as the density of water.
Yeah. You can make that assumption, but it's going to be off a little bit. So that's the case. You just, well, we're going to assume. It's like cool water. Is the density of cool water the exact same as pure water? No, but we're just going to assume it, otherwise we can't answer the question. All right, other questions?
Yeah. So when it comes to ionic and non-ionic compounds, I understand ionic tends to be with the metal and non-metal.
Unless it's ammonium or
Yeah, that's what I needed to remind myself because it was ammonium hydrogen phosphate.
yeah, then that's ionic because ammonium's an ion.
Okay.
Okay, other questions? So I posted an old exam on Canvas. Kind of like this, some multiple choice questions and then some free response. There's some nomenclature questions too. Can you bring a little Scantron for the multiple choice? There are 36 multiple choice. You know, those little ones, or just a regular size. Scantron for the test.
What number of Scantron?
What do they sell at the library? The two?
There's a two-sided one that's 15 questions on each. 82, I think it was.
They have the smaller ones too, the quiz size ones. You know those? This is fine, the 82E. Pretty good. Thanks. So we have a mix of multiple choice questions and then some free response here. Some of these are tough. Like number 39 here is pretty tough. Number 39 is stoichiometry problem. But it's not an easy, straightforward stoichiometry. It's a mixture. All right, let's take a break now then. If there's no other questions, we'll go on a break and then we'll start the lab after the break.
Does this say hands-on lab?
No, this is a demo. The first part's demo, and the second part's hands-on. We're going to be doing this lab over a number of lab periods. So chapter 4 is mostly just review. Chemical reactions and chemical equations, you know, just balancing chemical equations, and then stoichiometry, and then it talks about chemical reactions in solution. In solution, we talk about molarity and solution dilution, so that's also in section 4.3. 4.4 is determining the limiting reactant, and so we have limiting reactant, excess reactant, percent yield. 4.5 and 4.6 are just additional topics in stoichiometry. So it's mostly just review. There's not much of a difference between Chem 4 stoichiometry and Chem 1A stoichiometry, except Chem 1A, you could have more complex stoichiometry. There's a stoichiometry problem in chapter 3, which deals with a mixture of methanol and ethanol. Did anybody do that homework problem in chapter 3? The methanol-ethanol mixture?
Not there yet.
Not there yet? Okay, that's a kind of a tough problem.
Is that kind of the one that you were showing us in the practice test?
Yeah. Right. Oh, that's the one I was planning to do it in class. Let's see. I'll probably end up doing it tomorrow. But this lab, deals with chapter 5 tutorial. Yeah. The nature of aqueous solutions, 5.1. When we have an aqueous solution, aqueous just means dissolved in water. And so there are two things we ask ourselves when something dissolves in water. One, is it soluble? Will it dissolve in water? And so we can talk about that first. And then two would be electrolyte properties. And so let's take a look at solubility. We have the solubility rules. Experiment 17. We have two sets of solubility rules. The solubility rules for molecular compounds. Molecular compounds are compounds typically of nonmetals, like methanol. Methanol is a molecular compound. Some people think of methanol as an ionic compound because they see an OH. Usually if you see an OH, that means what? Hydroxide. And so is this methyl hydroxide? Yes or no? The answer is no. This is not methyl hydroxide. One, methyl is not a cation. Methyl is a CH3 with a bond to something.
It's an alcohol.
It's an alcohol, yeah. The difference between this OH and a hydroxide is this would be an ionic bond and the oxygen would be, this OH would be negatively charged. But this is covalently bonded. So this is a molecular compound. And the solubility rules for molecular compounds is very simple. We just say light dissolves light. So methanol is very much like water. Water can hydrogen bond, methanol can hydrogen bond. And so methanol fits right in with water molecules. Let's take a look at water.
As I'm in the midst of applying for residency right now. Hi, dropshippers. It's time to focus on what you do best. So go to Wix.com.
So this is called an ab initio. You know what ab initio means? Ab initio is just purely from theory. And so this is just based on mathematical calculations on theory. Do you see these purple things? You know what those purple things are? Pretty much hydrogen bonding and dispersion, but hydrogen bonding is a significant. And this is what causes the water molecules to stick together in the liquid. This hydrogen bonding interaction. Well, methanol just fits right into the crowd here. So if methanol is in here, it can hydrogen bond with water as well. Although, one end of this won't hydrogen bond. Can we hydrogen bond with the CH3 end? No, just the OH end hydrogen bonds. And so this is out of the place, but this is not so big. So even though it's a little bit different, it fits right in. And so if something fits right in, then those things are typically like what we call miscible. And in fact, methanol is miscible in water. What does miscible mean?
Dissolve.
It dissolves, but it does more than that. It's if something's miscible, it means it's infinitely soluble. So this has been slowed down. That 1 minute, 19 second video is actually just 1 picosecond worth of time. And so this is an ultra slow motion. It just means it's like water is miscible in water. And so you can dissolve an infinite amount of water in water. This is the same thing. Well, methanol is close enough. And so methanol, you can dissolve an infinite amount of methanol in water. And there's no limit to how much you can dissolve. Uh-huh.
How's it dissolving if it's the same size?
What's that?
How's it dissolving if it's the same size?
Because we can have like, I mean, you're right in the sense that we don't call it dissolving, we just call it mixing. But in another sense, it is dissolving. So if I have some water here, let's say I'll have some water here. We're going to call this the solvent, which is the major, and we'll call this the solute water. And so how much solute water can I dissolve in the solvent water? An infinite amount, because water just mixes with water. Well, that's kind of how methanol works. When you mix methanol and water, it's miscible. And so two miscible liquids you can just pour into one another. However, when we're thinking about solubility, there's two definitions for solubility. There's the qualitative definition. Qualitative definition goes by soluble or insoluble, or something right in the middle. Something right in the middle would be called slightly soluble. So we have S for soluble, I for insoluble, and SS for slightly soluble. Now the cutoff for the qualitative is 0.1 molar. If you can dissolve more than 0.1 moles of solute per liter, it's called soluble. If you can dissolve less than 0.1 moles of solute per liter, it's insoluble. If you can dissolve around 0.1 moles of solute per liter, it's slightly soluble. And so this is highly soluble. This would get the S here. Whereas methane is not. Methane does not hydrogen bond. Even though there's lots of hydrogen, why does methane not hydrogen bond?
It's already fulfilling the contract.
This is already fulfilling the octet.
There's too many.
So reagents here are used or already have their electrons taken.
Well, it has to do with polarity. When we say like, methanol's polar, water's polar. Not only have they hydrogen bond, whereas methane is non-polar. And so this is why it's unlike. So if you put methane in this crowd of water molecules, it doesn't fit in. It's going to be pushed out and it's just going to bubble out. And it's the same thing with oil. Oils would be pushed out of the crowd of water. It would not fit in. Whereas methane would fit into, let's say, an oily liquid. Then, yeah, it would fit in there. Then we have the quantitative solubility. The quantitative solubility is, yeah, methane might not fit in, but maybe a little bit gets trapped in there. And how much is that little bit? Well, the question of how much is quantitative solubility. You know, how many grams or how many moles can I dissolve of it? Well, for methane, it's going to be very little, but sometimes things, even though it's very little, are very important. Like oxygen. Is oxygen polar or non-polar? Oxygen is non-polar. So does oxygen dissolve in water? We'd say no, oxygen shouldn't dissolve in water because it's non-polar, water's polar, and therefore we classify oxygen as insoluble. Oxygen is insoluble, however, it's not so black and white, you know, because these kind of qualitative solubilities are more black and white. But even though it's insoluble, a tiny bit will dissolve. And that tiny bit that dissolves is very important for fish. Otherwise, the fish couldn't survive in water if there's no oxygen dissolved in water. So a tiny bit does dissolve. But qualitatively, we say it's insoluble. But maybe what we're more interested in is quantitatively. Even though most of it doesn't dissolve, a tiny bit does dissolve. And how much is it? If I want to know the quantitative solubility of certain things, what I do is I look it up. You know what some reference books are to look these types of things up? One reference book is this. This is You can find lots of data like solubility. Not only can you find solubility, you can find melting points, boiling points, colors, forms, etc. So the handbook of chemistry and physics. The only problem with this is it's expensive. It's updated every year. This is the 97th edition. And this is about $200. There's another book that's very common, and that's called the Merck Index. These books are complementary. The CRC Handbook of Chemistry and Physics, that deals mostly with inorganics, although you can find quite a few organics. Merck Index is published by the drug company, Merck. And since this is a drug company, they're interested in drugs and biologicals, like biological mixtures and other stuff, as well as some chemicals. And so this is good for organics and drugs and biologicals. But this is also an expensive book. You can find this at the library. What's that?
I think there's one in the camera.
Yeah, I think there's one in the camera, I'm sure. But normally where I go is just Wikipedia. Wikipedia, how much of it can you trust? Well, not much, but what I found from this is the data on compounds and substances is pretty good. And so these numbers are usually pretty good. I don't know if they update it every year. They probably don't. So the CRC and the Merck, those are updated every year, so you can see the latest data. But nonetheless, I usually look at, because you don't have to pay for this and you don't have to flip through a book, you can look it up pretty quick. So this is for sodium chloride. Sodium chloride is not an organic compound. It's an inorganic compound, and it doesn't form molecules, it forms what? Lattices. And so here we have a lattice of sodium chloride. Which one is the sodium, which one's the chloride?
Sodium's the green big.
The big one? Chloride's the small one?
No.
No.
What's the big one?
Sodium is the small one, chloride's the big one. There's a simple rule that you might try to remember. One is that cations are smaller than anions. Anions are bigger. There are only a few exceptions. And so that's a rule. It's not a law. You know, a law has to be more stringent. So rules can have more exceptions. Normally you would be right in thinking sodium is bigger. I'll put it. Normally sodium over here is bigger than chlorine. You know, as we go across the periodic table, the atoms shrink. And so the atoms get smaller and smaller. These are atomic radii here. So if we start at an atomic radius of 190 at sodium, as we go across, it shrinks and shrinks down to 71. So it's less than half the size.
So we're looking at sodium atom in its elemental form compared to the sodium in its cation form. That's why it's smaller.
Right. That's exactly right. And so the atoms shrink quite a bit going left to right. But what happens is we're not, in sodium chloride, we're not dealing with elemental sodium, we're dealing with sodium ion. And so what happens when we lose an electron? When we lose an electron, do you know what happens to the size? It shrinks and it becomes what? About, well, it becomes about half the size. So we go from 190 for sodium to what for sodium ion? Let's take a look at sodium ion. So the blue here is sodium, and the sodium ion is this dark circle here. The dark circle is 102. So we went from 190 to 102, about half the size. You see? And if you look at all the cations, can we make a generalization? When we form a cation, the cation is about half the size of the parent. And so when you look at it, more or less half the size. Some of these more, like silver here is a little bigger, gold quite a bit bigger. Some less, some are quite a bit smaller than their parent, but we can just say roughly about half the size. So cations shrink in size. Whereas, what do you expect for anions? For anions, when they gain electrons, the size doubles. Take a look at the anion size, which is the dark circle, versus the neutral element, which is the light circle here. You see it's about double the size? And so what happened is it inverted. So the sodium shrank to about half the size, and the chlorines doubled in size. And that brings us to the general rule. The general rule are the anions are bigger than the cations, with only a few exceptions when we look at this as a whole. So going back, when we have an ionic compound like this, metal and non-metal, does it form molecules? So for example, this sodium and this chlorine, is that a molecule of sodium chloride? Would we call it a molecule? And this thing is just a whole bunch of these molecules packed together? No, this type of bonding is totally different. This is ionic bonding. And so if you have a positive, you want as many negatives as possible around it. So if I look at this positive one on the corner, on the edge here, this one's going to have 1, 2, 3, 4, and a fifth one we can't see back there. If we look at a purple one inside the bulk, then there's 6. So we want to fit around this as many negative balls as possible. When you look at this one on the corner here. How many green ones does it have? It only has 1, 2, 3. So what that means is this one isn't as ionically bonded as this one. And so normally when we dissolve something like this, water attacks it. And so water dissolves this crystal, it's going to pull the corners first, because the corners are going to be the most loosely held. And then it's going to attack the edges. And then it'll attack the faces, and then it'll eat into the bulk of it. And so this is like a sugar cube. When you dissolve a sugar cube, do you notice the corners round first? The corner ones are going to be attacked first because they're the least bonded. In the case of sugar, it's going to be not bonds, but it's going to be intermolecular forces. And so it's going to be held the weakest in terms of IMFs. Well, anyway, going back to this, okay, so how much of this dissolves? Well, we know that it's soluble. Table salt soluble. That's qualitative, so it gets an S, it's soluble. But if we want to go quantitative, then we want to know how much of this dissolves quantitatively. And so this is the quantitative solubility. And so we could either say S for soluble, or we could just say this. 360 grams of sodium chloride will dissolve in 1,000 grams of pure water. So that's the soluble. It's also soluble in methanol. Methanol is kind of water-like. And 14.9 grams will dissolve in methanol per liter. There's no temperature here. Citation needed or clarification needed. The others have citation here, so you can look up the original source data. So the data in Wikipedia, this chemical data is pretty good, I think. Well, sodium chloride is not a molecular compound, so we would not use this rule. Instead, for ionic compounds, what is the rule? So we said oxygen's insoluble, but what is the solubility of oxygen in water? Well, it's insoluble I, but we want the quantitative solubility. So what we could do is we could just look it up on Wikipedia and see. 1, 2. Okay, so this is the limit of Wikipedia here. Wikipedia doesn't have the solubility here. And so we'd look for it in other sources. To find it. But these are some sources that you can look up for this kind of data.
Paramagnetic or magnetic mean?
Well, if it's attracted to magnets or not attracted to magnets. So paramagnetic materials would be attracted to magnets. And so oxygen's paramagnetic, it's attracted to magnets. So for something like sodium chloride, this is qualitative. And what we do is we take a look at the cation first. And so number one, group 1 and ammonium salts. And the anion can be anything. But if the cation is group 1 or ammonium, then these are all soluble. So ammonium phosphate, soluble. Potassium chromate, soluble. If it's not a group 1 or ammonium cation, then we look at the anions. Looking at the anions, we can look at acetates, nitrates, and chlorates. What's the formula for nitrate?
NO3 minus
Good. Acetate?
C2H3 O2 minus
And the chlorate?
COO3.
Good. These are all soluble. You might go, did you have to memorize these for Chem 4? Intro?
Yep.
Yes. Some people don't. They don't have to memorize. It depends on the instructor. But you go, I don't need to memorize these because I can just look them up. You can look them up, that's true, but what we want to do is, in science, we want to look for patterns. And so sometimes just the exercise of writing it over and over, you can start to notice some patterns. There's some patterns here in the solubility rules, and those patterns help us predict things that are not on the chart. And so it gets us to the next level. And so nitrates, acetates, and chlorates are all soluble, followed by chlorides, bromides, iodides. One pattern here is that fluoride's missing. Why is fluoride missing? Chlorides, bromides, and iodides are soluble, except which ones?
Silver.
Silver. What's the charge on silver? +1's correct. Is it variable charge or fixed charge? It's fixed charge at +1. There's only one charge with silver, and it's +1. Lead. What's the charge on lead? Is it fixed or variable? It's variable. And what are the two common charges for lead? 2 and 4. It turns out it's just lead 2. Lead 4 chloride is actually soluble. And mercury. Is mercury variable charge or fixed charge? Variable. And what are the charges on mercury? 1 and 2. Good. It turns out it's just mercury 1. Mercury 2 chloride soluble. And so this is Hg2, 2+. This is the mercury 1 ion. So looking at the transition elements up to copper are common charges are +2, +3. And then we hit copper. Copper is +1, +2. Silver is only +1. Gold is +1, +3. Zinc is It's only +2. Cadmium is only +2. Mercury is +1, +2. Then we go over one more column. Gallium +3, +5. Indium +3, +5. Germanium +2, +4. And so that takes us through the periodic table. So it's easy to remember if you remember the pattern versus, oh, I'll just look it up. You know, you can just look up the charges, but if you know the pattern, then you can figure more things out. They are. So why isn't fluoride here? Well, let's talk about that a little bit now. When we dissolve it, like say this is some lattice here, we want to dissolve it. The water is going to pluck apart the crystal lattice here. And one of the things that's going to impact the solubility is how strong the ionic bonds are. When we have an ionic compound, we have ionic bonds holding them. And ionic bonds are electrical attractions. If we have a cation, we try to fit as many anions around it as possible. If we have an anion, we try to fit as many cations around it as possible. When we're looking at electrical interactions, we like to look at Coulomb's law as just a crude picture of an ionic bond. Coulomb's law says that the force is proportional to the charge, the magnitude of the charge on cation A and anion B, divided by the distance between the center of the charges squared. When we do this, we don't really apply Coulomb's law to anything. Instead, we look at something called charge density. This is how we apply it. So if I have a chloride ion, it's like this, Cl minus. Is fluoride bigger or smaller than chloride? Fluoride's smaller. So if I have a fluoride ionically bonded versus a chloride ionically bonded, which one will be stronger?
Chlorine.
Fluorine?
No, chlorine.
Chlorine? Why would chlorine be stronger? So I have a cation. Let's just put a generic cation. Are cations bigger or smaller than anions? Cations are smaller, so I'll have the same size cation here. Which one is going to form a stronger ionic bond? Yeah, it's smaller, but it's not because of the valence. It's smaller because the valence electrons are closer. But the reason it's a stronger ionic bond is because these ions are closer to one another. Now you think they're closer, they're touching. Do you see they're touching here? And they're touching here. There's zero distance between the ions. Well, this distance is not the distance here in the gap. The distance is between the center of the ions, here and here. And the center of the ions here and here. So when we look at the distance between the centers, it's closer here than it is here. The way we think about that is in terms of charge density. So if I have a -1 charge spread out over this sphere, it looks like this, let's say. And so this whole thing is carrying this negative charge around it. What I have to do is when I have fluoride, I have to concentrate that negative charge down into a smaller volume. And so now we have a -1 charge, but it's going to be concentrated in a smaller volume, therefore it has a higher charge density. A higher charge density means it's going to be more interactive or reactive in the sense of Coulomb's law. And in other words, we call this electrostatic. The electrostatic attraction here is much stronger than the electrostatic attraction here. You guys see that? And it's because of charge density. This is a higher charge density. And therefore, a stronger bond. And so fluoride is omitted here because there are a lot more exceptions to fluoride. So if we included fluoride here, this list would grow a lot longer. But what we're doing is we're just trying to come up with simple rules. Simple rules because we don't want to memorize bigger charts. I mean, we can look at bigger charts here. Let me show you. Out of order. Like here's fluoride. So we can look at that. I mean, if we have fluoride, what we probably would do is not go to a big chart like this. What we probably do is just look it up on Wikipedia or the CRC or the Merck. It'd be a lot easier. I'm not going to memorize this chart. I don't want to do too much, so we're just going to keep it simple. Then there are lots of other solubility rules that we could use. All right, 4. Anybody remember what goes next? Sulfates. Sulfates, good. Sulfates are soluble except silver, lead 2, mercury 1, mercury 2, calcium, strontium, and barium. Good. So now these would form insoluble sulfates, except silver is borderline. Silver is what we call slightly soluble, so it may or may not dissolve or precipitate depending on the concentration. But the others should precipitate or not dissolve quite nicely. So the bond between lead 2 and sulfate is a lot stronger, because lead 2 is +2 and sulfate is -2. And so we're going to get, a +2 -2 versus a +1 -1 makes a bond, an ion bond that's 4 times stronger as long as the size of the ions are roughly the same. Okay, 5.
Is it carbonates?
Not carbonates. Carbonates come at the end. The what? Anybody?
Professor, is that RA plus?
Oh, Ba, barium.
Hydroxides?
Hydroxides, good. Hydroxides are insoluble, not soluble. So most hydroxides are insoluble. They have quite strong bonds, but you might wonder why it's Well, it's because of the small size. Oxide's quite small and hydrogen's quite small. Hydroxide's quite small. So these are insoluble except group 1 in ammonium, because we already had group 1 in ammonium up here. Group 1 ammonium and calcium, strontium, and barium. Okay, 6. After hydroxides, we look at sulfides. What's the charge on sulfide? 2-. Sulfides are insoluble except group 1 ammonium and group 2. And so if you look at the previous rule, magnesium is missing here. What happened to magnesium? Well, it turns out magnesium hydroxide is insoluble. Why is magnesium hydroxide insoluble, but calcium hydroxide soluble? It has to be the size, right? So if this were calcium, well, calcium, let's say it's this big. And so if calcium is this big, is magnesium bigger or smaller? Magnesium is smaller. And therefore, it's going to have a much stronger coulombic attraction to anions, like hydroxide. And therefore, the ionic bond between magnesium and hydroxide is much stronger than the ionic bond between calcium and hydroxide. And that makes magnesium hydroxide insoluble, whereas calcium is soluble. And barium is even bigger than calcium. And strontium, even bigger than.
So wait, when calcium, strontium, and barium is paired with hydroxide, it's soluble?
It's soluble. Right. And so calcium hydroxide, soluble. Strontium hydroxide, barium hydroxide, soluble. Sodium hydroxide, lithium, potassium, etc., soluble. Ammonium, soluble. Everything else, insoluble. So iron 3 hydroxide, insoluble. Seven. Okay, now we can do the carbonates. Carbonate is CO3 2-. Phosphate is what? And chromate. Chromate is CrO4 2-. So carbonates, chromates, and phosphates. These are insoluble, except group 1 and ammonium. Group 1 and ammonium, those are kind of big. The biggest cations are where? On the left side. On the far left, we have the alkali metals. And so those are the biggest cations. And they only have a +1 charge. Down here. And the cations get smaller as you go across, and then we hit the anions. Actually, the anions are quite big. This is confusing because we're looking at both the cations in neutral and the anions in neutral. How big are atoms? This is atomic radii in picometers. So what's the biggest atom that you see? Cesium. It has a 298 picometer radius. And so we'll double it to get the diameter. And so the diameter is about what? 600 picometers. Which one's the smallest? Helium is 31 picometers. We double that, we get 62, which is close enough to 100. And so atoms range in size between 100 picometers to 600 picometers. And so that's about how big atoms are. Or in angstroms, it would be 1 angstrom to about 6 angstroms in diameter. Now, cations, what we do is we cut it in half. Like cesium would be cut in half rather than having a 600 picometer diameter, it'd be about 300 or 150 radius. And so sizes play an important role. We need to know the sizes so we can get an idea about charge density and this type of stuff. We don't have to have all the numbers memorized, but we should have some reference numbers memorized. What is the size range of atoms? Then we could get even more detail. What's the biggest cation? What's the smallest cation? What's the biggest anion? What's the smallest anion? And then we can get other data. How much does it shrink as we go across? So up here we went from 190 at sodium all the way down to 71 at argon. But over here we went from 300 at cesium all the way down to 120 for radon. So it looks like it shrinks to less than half the size as we go across. And then as we go down, how big does it get? So up here we're at 53 or 167 for lithium, and then we go down to cesium. So each time we add a layer or shell, how much does it grow? And so, these are just general trends that sometimes we'll take a look at to get a better idea, how the size distributed. Okay, this is solubility rules. And then the next thing we look at are electrolyte properties. They aren't the same. And so we look at these separately. In terms of electrolyte properties, we have 3 types of electrolytes. Do you know what they are? Strong, weak, and non. And so we look at the difference between these. So for example, electrolyte, strong electrolyte is defined as what? I'm sorry, can you repeat that? Yeah, it produces good electrical conductors. That's good. Actually, there are 2 definitions for electrolyte. There's electrolyte that electrochemists use. And so for electrochemists, a strong electrolyte is an excellent conductor of electricity. But we use a slightly different definition. For us, a strong electrolyte, when dissolved, electrolytes are substances that dissolve in water. When the substance dissolves in water, it dissociates. Close to 100%. And so it breaks up into ions. And so what you could have is, depends. You could have a dilute solution of sodium chloride that barely conducts electricity. And so if you have water, it barely has any salt in it. Is it going to conduct very well? No, it's not going to conduct. Or you could have a concentrated solution of a weak electrolyte. A weak electrolyte partially dissociates. And this is in water? Yeah, in water. It partially dissociates. And so we could have a weak electrolyte that conducts better than a strong electrolyte because the strong electrolyte just might be too dilute to conduct electricity. Whereas a weak electrolyte, even though it only partially dissociates, it's much more concentrated. So it can give you better electrical conductivity. And so it depends on which definition you use. We're going to stick with this definition here for now. And then we have non-electrolytes. Non-electrolytes do not dissociate. And so I need to talk about how to recognize a strong electrolyte. What types of compounds are strong electrolytes? Ionic. Yeah, ionic. But usually we say soluble ionic compounds. Soluble ionic compounds I just call soluble salts. Soluble salts. Are strong electrolytes. What else is strong electrolytes? Metal. Like metals. Metals don't really dissolve in water. Acids. Not just any acids, strong acids are strong electrolytes. Yeah, some bases, strong bases. Let's stop here at the strong acids first. What are the strong acids? Do you know the 7 common strong acids? Just give me the formulas for the 7 common strong acids. H2SO4, sulfuric acid, HCl, hydrochloric acid, nitric acid, HNO3. We have hydrochloric here. What else? Hydro, not chloric, hydrobromic acid, HBr. Hydroiodic acid, HI. Chloric acid, yeah, HClO3. That's 6, one more. Not chlorous acid's weak. Hydrofluoric acid's weak. Hydroiodic, we have hydroiodic already. Carbonic acid's weak.
Not nitrous acid, right?
Nitrous acid's weak.
Acidic acid.
Weak. Acidic acid's weak.
Sulfuric acid.
Sulfuric acid, we already have. Number 1. One more. Phosphoric acid is borderline, but it's still considered weak. Phosphoric acid, phosphoric acid is close because phosphoric acid dissociates about 80% rather than close to 100. So it's up there. 80% is pretty significant.
Perchloric acid.
Perchloric acid. What's the formula for perchloric acid?
HClO4.
HClO4. Okay, now we got them. These are the 7 common strong acids. Why do we want to memorize the 7 common strong acids? The reason we want to memorize it is because if it's not one of these, then most likely it's weak. So nitrous acid, hydrofluoric acid, all those weak. There are some exceptions though, unfortunately. This is not comprehensive. So for example, selenic acid. Selenic acid is not one of these, so you'd assume it's weak, but it turns out selenic acid is strong, but it's not common. So we really don't have to worry about it. Nitrous acid's common, but it's not one of these 7, therefore it's weak, and that's correct. And strong bases are also strong electrolytes. What are the strong bases? Hydroxides, yeah. Any old hydroxide? So for example, iron 3 hydroxide, strong base? Yes or no? Iron 3 hydroxide. It turns out iron 3 hydroxide is not strong, it's weak.
Group 1.
Yeah, that's good. The strong bases are the soluble hydroxides. The soluble hydroxides would be the group 1. So lithium, sodium, potassium, rubidium, cesium hydroxides are all strong bases. And ammonium and calcium, strontium, and barium would be strong. So if I had, let's say I had sodium hydroxide, strong base or weak base? Strong base. Let's say I had magnesium hydroxide, strong base or weak base? Weak. So this is strong, this is weak. these are two household hydroxides. You can buy both of these at the supermarket. Sodium hydroxide, when you go there, what section do you look for this? I was at Ralph's the other day and saw it. Although, you know, I was looking for it by its normal name. Red Devil Y. You heard of it? Red Devil Y. I was looking for this in the household product section because this is a drain cleaner. Sodium hydroxide. They just sell pellets of sodium hydroxide. Drain cleaner. Sodium hydroxide. Hydroxide is very reactive. It likes to react with fats. It breaks bonds.
So dissolve air.
Yeah, it'll also dissolve air. Breaks up some of the bonds. The hydroxide gets inserted in there. So you can buy it as a Red Devil Y, or I don't know if Red Devil Y exists anymore. So when I was there, they had some other name, but they had a little drawing of a devil red. Anyways, however, magnesium hydroxide is not in the household section. Where's magnesium hydroxide located? Magnesium hydroxide is located like in the pharmacy kind of section because magnesium hydroxide goes by another name. And yeah, they don't call it you wouldn't go there and ask for some magnesium hydroxide. You go up there and you ask for milk of magnesia.
Where would baking soda fall?
In the baking section.
No, I just felt like a strong base or weak base.
Baking soda is kind of interesting. Baking soda is sodium bicarbonate, which has a formula of what? Bicarbonate ion is what we call amphoteric. And so this is a weak acid and it's a weak base. So you'd have to go to the weak acid, weak base, amphoteric section of the supermarket, wherever that is.
I believe sodium hydroxide is also like hair products.
Oh, is it? Okay.
They have some new ones that don't.
Yeah. Yeah, this is powerful stuff. So let's say if you ran out of magnesium hydroxide, magnesium hydroxide comes as a suspension. It's a pasty liquid. It's a pasty liquid because most of the magnesium hydroxide doesn't dissolve. So when you try to drink this stuff, it tastes really chalky. It's like drinking crushed up chalk. Yeah. And that's good because it's not going to kill you. Whereas if you ran out of magnesium hydroxide in your medicine cabinet, could you run underneath the sink and grab the sodium hydroxide? No, this will kill you. This is a strong base, this is a weak base. So it's a pretty big difference. So you wouldn't want to do that. Okay, as far as weak electrolytes go, these are going to be the weak acids. There are lots of weak acids. And so we aren't going to bother memorizing any of them. We're just going to assume that if it's not strong, it should be weak. And so acetic, nitrous, sulfurous, etc., weak. The weak bases, I'm not going to list these either. I mean, I talked about some, like magnesium hydroxide, but a lot of these others are better understood once we get to Lewis structures. And some heavy metal salts. Heavy metal salts. Heavy metal salts would be like lead, mercury. ourselves. So I have a question for you here. I grabbed this bottle here because the label wasn't pointed towards me, so I was wondering, what is that? Because I thought this was the distilled water. Looking for the distilled water this morning, so I grabbed this bottle because the label wasn't turned towards me, and you know what it was? Lead acetate. This is lead 2 acetate. And you see all this white stuff up here? I grabbed that with my fingers. And I thought, well, if I grab that, then I'm going to get lead poisoning. So I came over here and washed off my hand. I only washed it off for like 15 seconds. I should really wash it off for how long? 15 minutes, but I didn't want to sit there washing it off for 15 minutes. And it was so little, so I just left it on there. I didn't really leave it on there, but I left it only on for like 15 seconds. But that's okay because, one exposure to lead, I figure that's all right. It's not going to kill me. But if I did that every day, can you imagine that? You did that every day, and if you're a little kid and you're licking the outside of the bottle or something, eventually you're going to get lead poisoning. If you get lead poisoning, there's some therapies for that or therapeutic treatments for lead poisoning. Do you know what they are? One of the treatments is lead likes this anion called EDTA. EDTA is a 4 minus. EDTA stands for ethylene diamine tetraacetate. This is a gigantic anion and it contains 4 acetate groups attached to it. Acetates would be like some normal acetate, but it's bonded to some other stuff here. And this gigantic anion likes to just encapsulate the lead like a giant cage, and it cages the lead right in the center. And so we form this species, PbEDTA 2 minus. So this stuff is really good at encapsulating or capturing lead. When it captures lead, it's really hard. The lead can't break free from this cage. Completely caged up. There are 2 medicines for this. One is sodium EDTA. Sodium EDTA is Na4 EDTA. And then they have calcium EDTA also. Calcium EDTA is, rather than having 4 sodiums, it has 1 calcium and 2 sodiums. EDTA. The sodiums break off easily. Would the calciums break off even easier? Or with less effort? Or would they stick around more tightly? So the calciums break off even easier than sodiums? Or the calciums? And so in other words, I'm asking you this. A +1 Coulombic electrostatic attraction to EDTA versus a +2. We're going to ignore size. Just looking at charge, the size is also going to impact it. If we look at sodium versus calcium, it's a little bit tricky because they're in different periods. But here, which one should have just a stronger bond based on charge alone? Calcium. And so the calcium is going, what's the calcium going to do? The calcium has to be knocked away. So the lead has to come in here and knock the calcium away, and then the EDTA can encapsulate it. The 2 sodiums stay on here. And so sometimes to simplify things, they just call this Na2 EDTA. It's not correct. And calcium EDTA is called calcium EDTA, CaEDTA. That's not correct either, but that's pretty good way. And so, do you see the calcium inhibits the EDTA from behaving? It's like this. You know, which one do you think would make a more effective medicine? Sodium EDTA or calcium EDTA? Which one do you think is more effective? Which one would make a more effective drain cleaner? So if I ran out of drain cleaner, would you run to the medicine cabinet and get some milk magnesium and pour it down the drain? Is that going to be very effective? No, why not? One, it's not very soluble, so you're just pouring more solid, semi-solid in the sink. And two, we need the hydroxide to attack the grease or hair or whatever is in there to heat it up. And over here, is the hydroxide free to react? No, it's not free to react. And so this is not going to be a very effective drain cleaner. And so which of these two drugs would be more effective, do you think? Sodium EDTA. Does that make sense? But sometimes being effective, it can be too effective. If it's too effective, then the EDTA starts searching for other things to capture. So if you have sodium EDTA and it's ran out of lead, what's it going to attack next? Well, whatever it can attack. And so in your blood, what do you have? Well, you have sodium ions in your blood. You have what else? You have calcium ions in your blood. And so if the EDTA runs out of lead to attack, what's it going to attack next? The next 2+ cation, which will be calcium. And so you have to be careful. You can't do this over the counter. That is, you can't really take it because things have to be monitored.
Well, remember I asked you the other day about superacids? So those would be really strong electrolytes, obviously.
Right. Superacids are really strong. We'll briefly look at this article from the CDC. Deaths associated with hypocalcemia. Hypo means too low, hyper means too high. So hypocalcemia and chelation therapy. It's a little bit too effective. So there are two treatments. One is calcium EDTA. Just shown here as CaEDTA. The other is sodium EDTA, shown here, Na2-EDTA. The reason there are two drugs is one is let's say if you ended up drinking, if you mistook this, you thought this was water, and you just shoved it down. Then you're going to have an acute case of lead poisoning, like a high concentration of lead in your blood. And if that's the case, then you want a more aggressive treatment. A more aggressive treatment would be sodium EDTA rather than calcium EDTA. Calcium EDTA is, okay, I'm grabbing the bottle day after day, getting a little bit of lead. I'd only watch it for 15 seconds because I'm not really too worried about it. But if I did that every day, then I'd start to worry about it. And so the calcium EDTA would be more chronic rather than acute. However, that's for adults. For children, do you want both therapies? No, you probably want the more mild therapy, which is calcium EDTA. The problem with this is this. we'll just scroll to the conclusion. The problem with this is this: look alike, sound alike. Calcium EDTA, sodium EDTA, they kind of sound like the same thing, like sodium hydroxide, magnesium hydroxide. You know, if it was just labeled that and it wasn't labeled drain cleaner or milk magnesia, it was just sodium hydroxide, magnesium hydroxide, think of how easily those can be confused. Well, the same thing happened with sodium EDTA and calcium EDTA. And so this happened, there might be more recent cases. This is an old report from the CDC, but this is in Texas in February 2005. A girl, 2 years old, checks in to get chelation therapy because they had a high lead level, BLL. So they check in like 4 p.m. Everything's going fine overnight. Actually, not fine. I think late at night, early in the morning, something happened. And by the next day, they check in at 4 p.m. The 2-year-old girl checks in at 4 p.m. By 8:12 a.m. the next day, pronounced dead. Can you believe that? What happened? What happened was they accidentally grabbed the sodium EDTA instead of the calcium EDTA. So anyway, the CDC recommends that they just don't carry sodium EDTA anymore. And so that's like, okay, the supermarket recommends we don't carry drain cleaner anymore or something like that. Or maybe they should label it, drain cleaner versus not, something. But anyway, this just didn't happen once. This happened multiple times. Pennsylvania, 2005, 5-year-old boy, dead. Oregon, 53-year-old, dead. That's an adult, but still died. So, I don't know, the risk of lead poisoning or the risk of dying from hypocalcemia.
Which one was the one that scientists died from?
The mercury, methyl mercury, yeah. Oh, I'll talk about that maybe later. Yeah, that was a pretty serious one too. In that case, I would have wanted the sodium EDTA if there was a scientist who spilled mercury on them. The lead, I touched that. Okay, I didn't die. I'm okay. But there's a mercury compound, which is called an organometallic. This person spilled 1 drop on a gloved hand. It was not a single, it was a double gloved hand. 1 drop on the glove. Peeled off the glove, washed their hands, and still ended up dying from heavy metal poisoning. And it was quick. I think from the time of the drop to the time of death was about 2 weeks, something like that. It was quick. So in that case, you want something more aggressive. Well, anyway, we can go to non-electrolytes. Non-electrolytes, everything else. So, for example, methanol. Methanol, even though it has an OH, it doesn't dissociate. This is a covalent bond. It doesn't break when you dissolve this in water. So when you dissolve this in water, it just stays together as a methanol molecule. Methanol is very polar. It's very water-like because it has this OH, COH, and this can hydrogen bond to water. And so methanol and water mix quite nicely. One another. I have a simulation here. Oh, this is the earlier simulation, but if you throw methanol in here, methanol and water are good friends, basically, and you can doesn't mix quite well. I mean, one way of visualizing the water, you know, all these hydrogen bonding interactions is all good friends. However, methane is not, and so methane would be excluded from this. And so this is a molecular dynamics of water. I have a molecular dynamics of methanol, but it's a little older.
This morning, Star Farms veggie sausage. This choice
Little Chargington requires less routine maintenance than most of the gentlemen.
So you can see this simulation isn't as nice as the others. In this simulation, they use little sticks to represent the molecules. Oh, this is C18, that's not water. These are all ab initio type calculations. All right, so let's take a look at the lab. This is a multi-day lab, so we're just going to do parts of it. And this is our conductivity tester here. You've probably seen something like this before, right? And basically, we have a circuit here, but there's a gap here. And so the electrons need to flow, but they can't flow across this gap because it's just air, and air doesn't conduct electricity very well. And so when we're looking at electrical conductivity, you know, strong electrolytes should have good electrical conductivity. We have this symbol sigma for electrical conductivity, and so I'll just call it conductivity. The units of electrical conductivity are the Siemens, as in the semiconductor, you know, S-I-E-M-E-N. And the electrical conductivity is going to depend on three things. It's going to depend on N, mu, E. N is the number of carriers. Mu is the mobility of the carriers. And E is the charge on the carriers. And so if we have pure water, if I have pure water, the number of water molecules is large, so N is big. The mobility, even though, you know, they're kind of sticky, this is slowed down. You know, this entire thing is 1 picosecond. And so even though it looks pretty sticky and doesn't look like they're moving, the water molecules can actually move. When we think about motion, there are 3 types of motion. Do you know what the 3 types of motion are? Vibrational, rotational, and translational. Good. And translational means they can move from point over here to a point over here. It's going to take some time because these are too friendly, and so the water molecule is going to get stuck, but eventually they can move. This would be like a crowded room, a big party or something, and everybody's your friend. The water molecules need to move from one end to the other, but they can't move so quickly because they need to interact with each one as they go along. But eventually they'll move over. So that's translational motion. And then we have vibrational motion. If you keep track of the bonds, you can see them vibrating. Like this one's just vibrated in. This one's vibrating out. And so the bonds are vibrating in and out like this, and they're also vibrating like this. So if you watch some of these water molecules, you'll see this vibration and you'll see this vibration. There's one more vibration. I don't know if you can catch it here. We'll try to take a look. There are 3 vibrations that water can do. And then there's rotations. You'll see some of these water molecules rotate. So let's keep an eye on this and see if you can see some vibrations and rotations. So I see some rotations taking place. Well, and then let's see, I see some vibrations here. Let's follow that. You see that vibrating? Like this and like this a little bit. So we see some vibrations there. And some translations. Eventually it'll translate over. And so those are the motions of water. And so we have mobility. We have lots of water molecules, we have mobility. Should it conduct electricity? So let me plug this in. Let me just check if it's working. You know what this is? This is the graphite rod. Does graphite conduct electricity? Do you know? We can check it. Let's see. What do you think? Yes? Yes. Yeah. Graphite conducts electricity. So this is working. Graphite has, it's different. What conducts electricity in graphite are electrons. This conductivity is for electronic conductivity and something called ionic conductivity. Metals are great conductors of electricity. Metals have lots of electrons, they're mobile, and they have a charge, -1. And so we have electronic, and then we have ionic conductivity. And so let's take a look at, we don't have any distilled water. And so what I'm going to use is, I'm just going to use deionized water.
So, would diamonds be good conductors then? And then it's part of
Diamonds are insulators.
insulators.
Yeah. Diamonds have just as many electrons as graphite, but the structure is different. The electrons in diamond lack mobility. They're stuck in place. We'll talk about that quite a lot later. Okay, so water. Does water conduct electricity? No. Water doesn't conduct electricity. Why? Yeah, it's missing the charge. Where are the charges? All the water molecules are electrically neutral. But you might have learned about pH. What is the pH of pure water? 7. And pH comes from what? Acidity. pH is the power of the hydrogen ion concentration. If pure water has a pH of 7.00 at 25 degrees C, what's giving it the pH? Because the pH is related to H plus or H3O plus. So do you see any H plus or H3O plus in water? I don't see it here. But do you know there is some? It's very little, so we probably don't see it. And these are just parts of the water molecule. You can't see the rest of it. And so let's talk about water because of this. For sure, water is a non-conductor. It's an insulator. And so we'd like to call water a non-electrolyte, right? But somebody might argue that we should call water a weak electrolyte. And the reason they might argue that we should call water a weak electrolyte is because of this. If I have water at 25 degrees C, pure water at 25 degrees C, it looks as if all the water molecules have the same energy, doesn't it? it looks like every single one of these water molecules is moving along exactly the same as the others. But is that the case? It turns out it's not the case. Some of these water molecules have low energy. Some of them will have high energy. The bulk of them will have some energy around what you see here. And we call that, in other words, all the water molecules aren't identical. We have what we call a distribution of water molecules. And this distribution, the easiest way to see this distribution is by using a graph, because we can see the whole thing. Rather than following each water molecule, we'll look at the whole population and graph it. And so on the y-axis, we'll put the population. On the x-axis, we're going to put the kinetic energy. The kinetic energy is going to get this abbreviation, E bar K, or EK, for kinetic energy. Kinetic energy and temperature are related. And so if the temperature is at 25 degrees C, then the temperature is directly proportional to what we call the average kinetic energy. Our book uses E sub K for kinetic energy. This bar means average. So at 25 degrees C, we're going to have some fixed average kinetic energy. But actually, we're going to have a distribution. Do you know what this distribution looks like? This distribution kind of looks like a bell-shaped curve with a little higher energy tail. This distribution we call a Maxwell-Boltzmann distribution. What it shows is the entire population here. And most of the population will have this kinetic energy here. But there'll be a small fraction that have very low energy and a small fraction that has very high energy. This curve is very common. It goes by other names as well. The other names for this Maxwell-Boltzmann distribution curve is the thermal distribution. This tells us the thermal distribution of kinetic energy. So, for example, let's take a look at this one here. Let's say the green one is at room temperature, 25. If we cool it down, then the whole population shifts to lower energy. So the blue one would be at a colder temperature. If we heat it up, the whole population shifts to higher energy. And so the red one here would be at a higher temperature. Now, the average kinetic energy is actually on the shoulder. It's not at the peak here. It's off here. So the average kinetic energy for the green one equals 25. The average kinetic energy for the blue one is going to be lower temperature. The average kinetic energy for the red one is going to be at a higher temperature. So the temperature and the average kinetic energy are related, but when we look at it as a whole, it's going to show a distribution of kinetic energies like this. Now let's focus in on the high energy population here. So if we look at the high energy population here, there's going to be a cutoff here. And beyond this cutoff is like this. If you're in this room, they're going to be like, let's say there are 1 billion people at your party here. So if you have 1 billion people at the party, there are going to be 4 of them that are going to have enough energy that they're going to come in here and collide. They're going to collide with enough force to break bonds. And so what happens in water at 25 degrees C is this. There's going to be a small population here with enough kinetic energy to react chemically. And so an H2O collides with an H2O. These two H2Os collide, and what happens is this water plucks one of the hydrogens off the other water. So we end up with H3O plus, and this water loses a hydrogen, and we end up with hydroxide. So we form hydronium and hydroxide. Now, there are different ways of determining the amounts here, but the amounts here of hydronium we're going to get is 1.0 times 10 to the minus 7 molar. So if we form 1.0 times 10 to the minus 7 molar of this, we're also going to form 1.0 times 10 to the minus 7 molar of this. This is just basic stoichiometry here. This is going to be at 25 degrees C. This 7 is the power of the hydrogen ion concentration. So the pH here is 7.00. And that's pure water. And so in pure water, we have some dissociation. We have what's called autoionization. Most of the water molecules won't, because most of the water molecules don't have enough energy. Just a small fraction of the water molecules will. So should we call water a weak electrolyte? Weak electrolytes partially dissociate in water, or should we call water a non-electrolyte? What should we call it? Because it certainly didn't. Did it light up the bulb? No, it didn't light up the bulb. We have charge. We have mobility. You know, these are going to make their way. Hydronium will make their way through here, and hydroxide will make their way here. So there's mobility. We have charge and mobility. What we're lacking in terms of conductivity is the number, the population. And so it turns out the population of this is so small, it doesn't really conduct any electricity. And so we can see that again here. Let me plug this in. And we'll try to turn off the lights to see if we can see any kind of, we're just looking for the faintest. You see anything? No, I still don't see anything. Here.
Maybe if it's at 25 degrees C, we'll see.
Well, this is close enough to 25 degrees C. How about tap water? So I'm going to put some tap water in here. Does tap water conduct electricity? Do you see that? So tap water is conducting electricity, but our DI water is not. But we know our pure water has a pH 7. If it has a pH 7, then it has some hydronium. If it has some hydronium, we must have had autoionization. And so this is pH 7. And so this means that it's not enough. Not enough. So, but I don't know, should we call it a weak electrolyte or should we call it a non-electrolyte? Do you know what we call it? We call it a non-electrolyte. We call it a non-electrolyte, but some does dissociate. It's just too little. And it's about 4 parts per billion. So if I have a billion water molecules, only about 4 of them react. And that's too little to call a weak electrolyte. And it's too little to conduct electricity. And conducting electricity, the way we usually measure the purity of the water is the conductivity is inversely proportional to the resistance. The resistance is ohms. And so if it's mega ohm resistance, then when we say it's an insulator, so pure water is an insulator, even though it has a tiny, tiny bit of ions present. All right, well, I'll stop here since I'm out of time, but I have my office half hour now, so you can stick around if you have some additional questions.